A potential energy curve is a tool commonly used to analyze the motion of an object. It graphs the potential energy as a function of the position of our object. You will always have a line, typically some sort of curve on a potential energy curve, or potential energy graph, you could say. In this video, we'll introduce you to how to analyze those graphs. So for starters, we need to remember that there's a relationship between force and potential energy. The way that we've looked at it before was that the potential energy of an object was equal to the negative integral of f dot dr. Well, we know that to kind of undo the integral, we take a derivative of something. So, in other words, if I'm given the force of an object, and let's say it's specifically a one-dimensional force, so it's the force in the x direction, that helps me get rid of the dot product over here. We're going to say, let's say our object is moving only in the x direction. Well, then to undo an integral, I use a derivative. So if I am looking for force and I'm given energy, then it's the negative integral of du dx. Sorry, negative derivative of du dx. That's important for us to know. This is something not on your equation sheet, but something you will need to know for the AP test. And the reason this is important is because we know that derivatives correspond to the slope of a graph. So if I have a energy, potential energy specifically, versus position graph, as I do here, I can find the slope of that graph, and the negative slope of that graph is equal to the force. That's one important way of using these potential energy curves. You'll also notice something that's commonly included on a potential energy curve is a straight line that tells us about the total mechanical energy of our object, like you see here. We know that an object's total mechanical energy is a set value. It can never magically gain energy, and if all the forces acting on it are conservative, it can never lose energy either. So taking a look at where this total mechanical energy line corresponds with the graph of my potential energy helps me know some things about the motion. For example, you'll see that this portion before x1 on my graph is above this total mechanical energy line. That tells me that the object can never actually reach any location that's to the left of x1 because it doesn't have enough energy. A force would have to do work on my particle or on my object to get it up to these values, to get it up to anywhere to the left of x1. I can also take a look at any of these other values and know how much kinetic energy my object has, because mechanical energy is the sum of kinetic and potential energies. You'll see that marked on the graph quite a bit. So, for example, at x2, the potential energy is 0, so that means all of its energy is kinetic energy. See, as you see right here. Or, for example, at x5, or any location to the right of x5, the potential energy is 4 joules, which means it must have 1 joule of kinetic energy. A couple of other important things about these potential energy curves. We'll take a look at a couple of different examples of these. So anytime that you have a turning point, a point where an object changes going from one direction to another, that would be a point where your potential energy curve intersects with your total mechanical energy line. We know that because at that point, there's no kinetic energy, so all of its energy is potential energy, which means it's not moving, and that corresponds to a turning point. Additionally, anytime that you have a maximum or minimum on your potential energy curve, for example, at a point like here on x2, or a point here on x3, those are what are considered to be equilibrium points. There's two types of equilibrium points, stable and unstable. If you have a U-shaped, so it's a minimum in your graph, that's considered to be a stable equilibrium, because if I were to displace my particle slightly away from x2 in either direction, then it would return back to x2. Whereas x3 would be considered to be an unstable equilibrium, because if I were to displace it slightly away from x3 in either direction, my object would kind of fall down into these wells, so would not return to my equilibrium point. So let's take a look at an example using these potential energy curves. This problem is number 38 in your textbook. It's a graph showing the potential energy at certain locations on the x-axis. So notice that this is x in meters, and here's my potential energy values. To make sure that you really understand these potential energy curves, please complete this problem for homework and bring your work and your answers with you to class when we meet.